About 1,000,000 miles from Earth, there's an infrared observatory sitting in space, orbiting the distant recesses of the solar system. It's been 7 months since the James Webb Space Telescope left the confines of the Earth to make its home at the Earth-Sun Lagrange point. And now finally, NASA has something to show for the $10 billion investment. As of now, NASA has shared 5 images from the telescope, and their resolution exceeds the greatest expectation. The JWST is more than just looking back into the cosmic history. It is exploring the origins of the universe, and quite possibly the origins of life as we know it. These pictures capture a nascent and primitive universe, but they can also measure the chemical makeup of the atmospheres of exoplanets, and, if we're lucky, one of these planets will have the chemical framework to support life. The key to finding preliminary signs of life in the universe comes from the efforts of astrobiologists to read biosignatures coming off of different planets. If a planet has an atmosphere that can support even the rudimentary forms of life, then this can be discerned from investigating how starlight interacts with the planet's surface. These nuances in light can be picked up by the JWST. But what does light have to do with the possibility of life? Every object interacts with light to some capacity, absorbing certain wavelengths and exuding others. Think of chlorophyll, for example. The green pigmentation of plants comes from chlorophyll's ability to absorb reds and blues in the visible spectrum and shoot back the greens, which is what we end up seeing. Now, the same thing is happening with planets. The atmosphere of planets have a disproportionate distribution of gases, and since all gases interact differently with light, we know the chemical makeup of the atmosphere. Earth, for instance, had very feasible biosignatures 2.4 billion years ago because the landscape was dominated by volcanoes that left carbon dioxide in their wake. But with the evolution of a family of algae, the amount of oxygen in the air became a major constituent, and since oxygen absorbs different wavelengths than carbon dioxide, the light coming from Earth would have changed. This is the exact principle that astrobiologists apply when they are trying to ascertain the possibility of life on a certain planet. Patterns in missing light can reflect specific compositions of gases in the atmosphere. Now, the JWST is better than its predecessors in the fact that it relies on infrared light as opposed to visible light. This allows it to detect light with wavelengths anywhere from 0.6 microns to 28 microns. Unlike the Hubble Space Telescope, which detects light in the visible spectrum, the JWST can see past dust and clouds in space that get to the light coming from distant stars and galaxies. Because of this, it was able to identify WASP 96b, which is an exoplanet some 1,150 light-years from Earth. This puffy gas giant has a crispy temperature of 1,000 degrees Fahrenheit, but showed distant signatures of water vapors in its clouds and haze. Though the temperature and the size make this planet inhospitable, the mere fact that the JWST can identify and analyze atmospheres light-years away is impressive and will no doubt pave the way for some major breakthroughs. Another key factor which determines whether a planet would be suitable to accommodate humans is the terrain. Several of the 5,000 planets that have been identified are tidally locked planets. This means that they complete an orbit in the time it takes them to revolve around their axis. Planets which orbit red dwarf stars are particularly susceptible to tidal locking because of their core proximity to their star. Closer to home, we can see tidal locking in the orbit of the Moon, which has one side of its face constantly facing Earth, which we've referred to as the near side of the Moon. Now, a planet like this has some serious unsustainable issues. It would mean that for a long period of time, only one half of the planet would be receiving sunlight, while the other half is gripped with perpetual darkness. Now, this might seem like a serious red flag when it comes to finding a habitable planet, but there are still chances that it could sustain life. A good defense for a tidally locked planet is that their terrain dictates how well they are able to absorb and distribute that heat to distill parts of its surface, the far side. If it can perform this conduction successfully, it could easily create a homogeneous surface temperature that would prevent things from getting either too hot or too cold. But how will it accomplish this? A planet like this hinges on 2 key factors: the amount of land and location of that land. A steady balance of land on either hemisphere is likely to keep the balance of temperature in check, keeping it at a healthy 36 degrees Fahrenheit. It doesn't matter whether the land is packed near the equator or closer to the poles, as long as the distribution is even. Adequate convection and conduction can occur to maintain a healthy temperature. There also has to be a sizable ocean on at least 60 to 70% of the surface. Otherwise, the land would become too dry, and due to lack of evaporation and precipitation, the temperature would spike. It would have a desert climate. So the ideal tidally locked planet would need to have a sizable ocean on its daylight side and land on the far side. This would facilitate evaporation, and since water vapor is a greenhouse gas, it could carry heat energy over to the other side of the planet. Up until now, the telescopes used did not have the resolving power to scrutinize the surface of exoplanets. The JWST might not be entirely capable of that either, but it does offer a clearer picture of a planet's atmosphere, which means that it could play a critical role in the analysis of its terrain as well. If we confine ourselves to our galaxy, the Milky Way, astronomers have deduced that there are nearly 300 million potentially habitable planets. But because of the limitations in technology, we have been able to identify only 5,000 of such exoplanets. These planets orbit in a Goldilocks zone, which means they aren't too close to their sun to get fried, and they aren't too far away to freeze over. Unfortunately, the small number of discernible exoplanets and their distance from Earth have made them very difficult to study. But the JWST can change all that by giving researchers a magnifying glass to analyze these planets more closely. In 2018, astronomers found that of all the exoplanets scrutinized by now, one of them showed particular promise, insofar as it resembles Earth the most. The planet was named the TRAPPIST-1e. If we were to look for a habitable planet, this would be a very worthy candidate. The TRAPPIST-1e is part of the TRAPPIST-1 system. The TRAPPIST-1 is an ultra-cool dwarf star, which basically means that it is cooler than our own sun. The distance between the TRAPPIST-1e and its sun is less than an astronomical unit, but is still in the habitable region. In almost all respects, closely resembles Earth. The problem, though, that astronomers have faced is determining the composition of its atmosphere. They were uncertain whether it contained oxygen and carbon dioxide like Earth, or methane and sulfur dioxide like Venus, or indeed, whether it had an atmosphere at all. Everything that they know about the planet comes from either speculation or simulation, but for conclusive proof, they would need to take a closer look. The JWST can aid in just that. Since it can determine which wavelength, or rather, lack thereof, is coming from a planet, it can draw up a list of the key ingredients in TRAPPIST-1e's atmosphere. The telescope is actually observing the TRAPPIST-1 system as a matter of priority to finally quench the curiosity that has plagued scientists since it was discovered back in 2018. Determining a habitable planet by just its atmosphere is a bit of a gamble. There are many more factors taken into consideration. An organism could be responsible for the emissions of methane into the atmosphere, but then so can volcanic activity. Oxygen could be a byproduct of photosynthesis, or it could be from the photodecomposition of water. You can never really know definitively whether the planet deemed habitable is genuine or just another false positive. For a planet to be habitable, it needs to have three things: liquid water, a solid surface, and a thin atmosphere with certain gases. So far, the TRAPPIST is their own viable candidate, but we'll need to wait until the JWST can prove conclusive proof. If you guys found this video informative, be sure to hit the like button and subscribe to the channel for more content just like this. And as always, thanks for watching.